Hi, everybody out there in podcast land. This is Mr. Folly again, and welcome to podcast 12.1. This looks like an awful lot of stuff. I don't think it'll be too bad, but we'll see. This chapter is called kinetics, so I'm going to give you a definition of kinetics. Talk about relative rates, and kinetics really is kind of the rates of reaction. There's your definition. Based on coefficients. Remember, coefficients are the numbers in front of something. So if I had 2 NaCl, the 2 would be the coefficient. We're going to look at rates in terms of change in concentration over time, looking at how reactions occur in steps, what an intermediate would be, how catalysts look in this type of examination, define and look at rate determining steps, look at the new equation for the rate law, and then look at graph interpretation, which is kind of the beastie of this part. So let's go ahead and hop into that. Kinetics, how fast a reaction occurs. Reactions can be unbelievably fast, like an explosion. Boom! Mummies decomposing. Remember, the mummies are thousands of years old. You can still go to the museum and see the little mummy and his little, white rags or whatever it is. And buildings erode. That's very, very slowly. So you do want to control how fast reactions happen. If you can make your product, say you're a chemical company, and you can make your chemical faster, you can make more money. Here's an example of a reaction. 4 Fe plus 3 O2 yields 2 Fe2O3. If 4 moles of iron react, how many moles of oxygen react? So if it's 4 and it's 3, that would be 3 moles. If 2 moles of iron 2 oxide form, okay, same as the coefficient, if 2 moles form per minute. So now I've made it a rate. So now it is 2 moles per minute. Now it's a rate. How many moles of oxygen disappear per minute? So again, if this is the coefficient for iron 3 oxide, then the rate is going to be 3 moles per minute. So it doesn't mean 3 moles will react, it means 3 moles will react per minute. If oxygen disappears at 5 moles per minute, what is the rate of change for iron and iron 3 oxide? So what I'm going to do first is do 5 moles per minute of O2 times dividing bar. So this would be 3 moles of O2, coefficient. For iron would be 4 moles of Fe. And then notice moles of O2 would cancel out, and I would get 20/3, whatever that is, moles of iron per minute. And then pretty much the same thing for Fe2O3, 5 moles O2. You should never leave it in this form. You get a decimal. I don't have my calculator. Moles of O2 per minute times 2 moles Fe2O3, 3 moles of O2. And that would be 10/3. And again, use your calculator. 3.33 is what I should say. Moles per minute. All right. One way to look at this graphically is, hopefully you can see this. Let me darken these lines a little bit. Hopefully this is a green line. This is NO2 for this reaction, so that's NO2. The other one is purple. Let's see if this purple one would work. This purple one is NO. And then the last one is gray, so let's see if we can do this, which is probably not at all gray. But gray would be the oxygen. Okay, so looking at this now, how do the coefficients affect the curve? The bigger the coefficients, right, the steeper the curve, right? So specifically looking at NO and O2, didn't NO go twice as fast? How do coefficients affect the curve? They act as a multiplier. Where do the reactants start? So NO2 is my reactant. The reactants start They start where? They start high. Products start where? 0. And what happens to the flat part? Does that mean the reaction stops? No, the reaction doesn't stop. That means the reaction is at equilibrium, which means what happens is the reaction is going both ways, and it reaches a spot where it doesn't stop, but it's going back and forth. So you should be able to analyze a graph like that. So again, reactants start at 0. Products start with some number. Let me start again. Reactants start up high. Products start with none, and then they change as they go. Rate is measured in concentrations per time unit, usually molarity per minute or molarity per second. We wouldn't use anything besides molarity, the other ones that you just learned. Reactions occur in steps. If I had one step, A goes to F, or F minus in the case of some of the most gifted. This is an elementary reaction because it has one step. A plus B yields C is elementary. Why? It has one step, and that's it. For this reaction, A plus B plus E yields G. This has many steps. A plus B yields C plus D. Then D reacts with another reactant, E, to make F. Okay, so right now, notice how D was a product and then it's used up. That means D would cancel out. Okay, so when I say D is an intermediate, it cancels out. That means it's created and then used up again. F also would be in the same situation. You make F, then you use it again. Okay, now over here again, also notice C is created and then it's used up. So C and D are intermediates. I missed another intermediate. That intermediate would be the F. Okay. So multi-step reactions are way more common than elementary reactions. Catalysts speed up a reaction but are not used up. So the way I look at a catalyst is it's something that helps the reaction happen. So if I ask you to cut a loaf of bread with a knife and nothing else, you're actually standing there with your loaf of bread and a knife, and when you try and cut it, it's hard when you don't have anything to cut it on. So my example of a catalyst would be if you have a table, you can put the bread on the table and cut it easier, or a cutting board where you can put it on the cutting board and cut it easier. Okay. So a catalyst will speed up a reaction that's not used up. Do you kill the table by cutting bread on it? No. Looking at the reactions in steps like we did before, A plus B yields AB. AB, notice AB would be a what? An intermediate. So, and then that produces A plus C. And then C yields D plus B. So again, C's product and then used up. So what is my overall reaction? So I know AB cancels out. I know my C's cancel out. So then I'm left with A. Oh, look right here. This is kind of odd. A starts out and then it's reformed. So wouldn't A cancel out as well? Yes, but A is a reactant and then a product, so it would be a catalyst. So my overall reaction would be simply B yields D plus, okay, so that's a bad example. B, because it shouldn't make B again. Let's make this a Q. Okay. Sure, write that down. Get your extra credit point. I had the wrong thing on there. Get it, get it, get it. B is a reactant and a product. It cancels out too. Whoops, I did that wrong. It cancels out too. Well, let me go back to what I had before. B is a reactant and a product. It cancels out too. So you know what? This is a really bad one. But you get the idea, I hope. But this needed to make D. Basically, I messed up and I made two catalysts that I reformed. So Mr. Fowley made a boo-boo. So we'll talk about that in class to make sure it's okay. A catalyst slows down a reaction without being used up. And you want to have, not a catalyst, an inhibitor slows down a reaction without being used up. And you want this sometimes. You want to slow down the reaction of food spoiling, that you can eat your Twinkies even later. Rate determining steps to the slowest step. If I'm making a cake, and I were to list the steps of making a cake, number 1, you have to mix the batter. Number 2, you have to cook it. And number 3, you have to frost it. Let's pretend that's all it takes. Mixing it takes 2 minutes. Cooking it takes 20. Or baking, or whatever you want to say. Frosting it takes 2 minutes. Okay. If I had to make 10,000 cakes at my house, it would take how long? Would it take 22 minutes or whatever it is? The slowest part, as soon as I make my mix once, then I have to, as soon as I've got my mix down, once I start cooking it, I can make a whole bunch of other mixes, right? I can make 10 more, 9 more, whatever it is. And then as soon as that's done, as soon as it's done cooking, I can frost just one cake. So all the time I'm waiting for my cake to be done. So the thing that determines this is how fast it takes to bake the cake. So what step would a catalyst affect? The slowest. step. So let's pretend I could use a microwave instead and I could cook it in 3 minutes. Doesn't that substantially change the time it takes to cook 10,000 cakes? What if I found a way to frost it in 1 minute? Would that have a huge effect? No, it doesn't, because that's only added once, to be honest with you, while you're waiting. Rate laws. A law is a mathematical equation. Rate equals k, a to the x, b to the y. And the equation would be ma plus nb yields c. So notice we only care about the reactants, and your coefficients are not. X and y are not coefficients, or let's look at it this way. M and n are coefficients. Coefficients do not determine these exponents. These are not coefficients specifically. So there's the rate law. So rate is impacted by some constant, and then how much of each reactant you have. So how do you find x and y? How do you find those exponents? You got to look at a rate table. If the change in the reactant is the same as the change of the rate, x equals 1. So for example, if something doubles, so if my concentration doubles and my rate doubles, 2 to the first equals 2. If the change of reactants has no effect, then x equals 0. So 2 to the 0 equals 1. If the change of reactant is anything else, x equals 2, and we'll look at those math things in a little bit. Initial rates from 3 experiments. So here's what we're going to do. In order to figure out the rate law with respect to rate equals k, NH4 positive, and then NH2 negative. In order to find this one, what I want to do is find NH2 negative. I want to find something where NH4 is the same. This way I'm only changing one thing. So in this case, this is times 2. And this is, if you can't do this in your head, shame on you, times 2. So 2 to some power x equals 2. 2 to the first equals 2. Or you can say they're the same, right? Both of them are times 2, so you're a winner there. To figure out NH4, you want to find something where the guys are the same. So NH2 is the same, experiment 3, so this is times 2, and the rate is also times 2. So 2 to the first is 2, so this one's also first order. Let's do another one. Same deal, and this time we've got more. If I want to look at the bromate's effect, then I want to find something where these are the same and these are the same. Nice. This one's times 2. This is, ooh, look at that exponent. 8 times 2 is 16, but it gets smaller, times 2. So my rate equals k times bro, and that's just the first power. Let's look and find one for Br negative. So Br negative. So I want to see where Br negative changes and the other ones don't. So do you see in experiment 2 and 3? The other guys are the same, and this doubles. And the rate here also doubles. So Br negative to the first. Then I have H positive. And I'll find one where H positive changes and the other ones don't. So 1 to 4. Those are the same. And this is times 2. And this is times 4. So that's different, so it's second order. 2 to some power x equals 4. X would be 2, that's why that one's second order. All right. Remind me in class, this will be the problem we do first thing. Yay! So we'll be all set in class so that I can be done when these guys take their tests. So now to review. Kinetics looks at rate. That's basically it's the study of rate of reactions. Reactions occur in steps mostly. Of course, there's a few elementary reactions, but not many. The slowest step determines the rate. Intermediates are formed and then used up. Catalysts are reactants and then products. That's how you can tell in those little step reactions. Rate equals k, a to the x, b to the y, and the x and y are not coefficients. Analyze the charts. You need to be able to analyze charts for 0, first or second order. More practice in class for this, and we didn't do a 0 one yet. So we're out of here in under 15 minutes. Woohoo! Have a good one. See you tomorrow.